Hello and welcome to the online learning video on chapter 15.1, graphs and level curves. This section will be about visualizing general functions of two variables in three-dimensional space, similar to quadratic surfaces, except now more generalized, because we cannot do calculus on functions of two variables if we can't visualize them. So recall that Rn is n-dimensional Euclidean space. So R is just shorthand for R1, is the real number line. R2 is the two-dimensional Cartesian plane. And R3 is three-dimensional Euclidean space, which is what we've been working on for most of this class. And recall that a function assigns to each point in the domain an output number z in what we call the range of f. And here's a visualization of it. You have a function f, a domain, and now here the domain can be both x and y, a coordinate, and it assigns to each coordinate point in R2 an output in R, which is like the z-axis. And we also sometimes say that f, the function f, is a map, and it maps each point xy to the point z. So we know that x squared plus y squared plus z squared equals 4 describes a sphere of radius 2. And solving for z, we then have that z is plus or minus the square root of 4 minus x squared minus y squared. And taking just the positive component, we can consider the following function. What is the domain of this? So this is new. You've found domains of functions in previous classes, but those were domains of functions of one variable. However, our strategy is still fundamentally the same. We look for where the function breaks. So for this function to be defined, we know that the thing underneath the square root must be greater than or equal to 0, can take the root of a negative, and then rearranging, that means that x squared plus, well, negative x squared minus y squared is greater than or equal to minus 4, and multiplying both sides by negative 1, we have that x squared plus y squared is less than or equal to 4. In this last step, we need to recall that if we multiply by minus 1, then it swaps the inequality. Okay, and what is this? Well, that is the inside of a circle of radius 2. After all, a circle of radius 2 is x squared plus y squared equals 2 squared. And this is saying that our x and y must lie inside of that, they less than or equal to 2. So that is the domain of this function. So a function of two variables whose output is a real number accepts a pair x comma y and outputs a single number z. And we can visualize this as a wavy sheet over the xy plane, whose height above each coordinate xy is the output z. So for each xy, we go up to some point, and if the function is continuous, then it won't have any breaks or gaps, and it will be a wavy sheet of some kind. And in fact, planes are, well, one of these functions. Many of the quadratic surfaces that pass the vertical line test are functions. And a function has exactly one output for each input. In contrast, though, a relation does not necessarily have a concept of an input or an output. It's just a relation among two or more variables. So, for example, this ellipsoid is a relation among x, y, and z. This looks like it might be something like x squared plus 2y squared plus 2z squared is 1, maybe, something like that. This is a relationship among x, y, and z, but it does not define a function. When you try to solve for z, then you get a plus or minus. There's not one unique output for each input, and that is reflected in the vertical line test, showing two outputs for a single xy input. So because a function has exactly one output for each input, the graph of the function must pass the vertical line test. So for example, this elliptic paraboloid, that is a function. Each input x comma y has exactly one output. And to be clear, functions are a special type of relation. Every function is a relation between the input and output. It's just that some relations like this one have multiple quote outputs for each input or for some inputs. So example, is the graph of the hyperboloid of two sheets, z squared minus x squared minus y squared equals 1, the graph of a function? We can do this by trying to solve for z. And doing that, we have z squared is 1 plus x squared plus y squared. And then z is plus or minus the square root of 1 plus x squared plus y squared. And that has two outputs for each input. So that is a no, it is not a function. It is a relation among x, y, and z, though. However, we can restrict this plus or minus the square root of 1 plus x squared plus y squared to just the top half by just taking the positive part. And then it becomes a function. Now there is one output for each input. So in this picture, that is the upper sheet of this hyperboloid of two sheets. The lower sheet would be down here facing down, but we have cut that out by eliminating the possible minus. And what is the domain of this function? Take a moment to think about that and pause the video. Okay, so we know that this guy must be greater than or equal to 0 since it's underneath the square root. So we're asking the question, when is 1 plus x squared plus y squared greater than or equal to 0? Well, this guy is always positive. It's always positive because 1 is positive and squares are always positive, non-negative technically. And that means that the domain is all of R2, the entire Cartesian plane. Every input everywhere on the xy plane has an output. Now, we're going to be talking about level curves. And level curves are really the curves in topographic maps. So we'll be understanding functions through making a kind of topographic map of them. Here is a topographic map of the Prescott area. There is Yavapai College. And each of these curves is a level curve in the sense that it's of constant altitude. So in this way, we can visualize the shape of hills and mountains and valleys by looking at the level curve. And the level curves here are of constant distance, vertical distance apart. So the fact that these lines here are very close together, that indicates steepness, while over here, those lines are far apart, and that indicates that it is changing altitude at a slower rate. So level curves are those curves of constant altitude. And there's a subtle distinction between contour curves and level curves. A contour curve of a graph, those are the intersections of the graph with horizontal planes, as depicted here. So we take various horizontal planes, each of those is a contour curve. And if we project those contour curves down onto the xy plane, then those guys are level curves. So the only difference between contour curves and level curves is that contour curves actually live up along with possibly non-negative z components, while their projection down onto the xy plane is a level curve. So when you look at a map like this one, all of these are level curves, not contour curves, because they're projected down onto a two-dimensional map, like the xy plane. Yeah, so level curves are like a two-dimensional topographic map, while contour curves are the actual curves of constant height, to which the level curves correspond. And looking at the level curves of a function, we can then piece together what the actual function looks like by visualizing what the contour curves look like from the level curves. So these level curves here correspond to this three-dimensional graph. And we want to be able to read level curves. Now, to be able to read level curves, we need labels for the z altitudes to which different level curves correspond. So here are various level curves, and we see that here z is increasing as we move from one level curve to the next in this direction. So piecing those together, we can see that the overall function might look something like this, as these are the corresponding contour curves to which they correspond. So what kind of quadric surface do the level curves at left most likely correspond? I know there aren't labels here, but let me do some labels. So here, the level curves, I'll say that z is decreasing in both of these directions, while in these directions, then z is increasing. So take a moment, try to piece together what the contour curves and thus quadric function look like, and identify what the quadric function is. If you thought it's a hyperbolic paraboloid, then you got it right. So we have various parabolas here, and the parabolas are decreasing in z altitude there, while the parabolas here are increasing in z altitude. And this intersection here, that corresponds to the saddle right there, which is, well, another level curve. And here the two level curves intersect each other. So to find level curves for a particular function, we simply substitute z equals z naught, very similar to the traces. In fact, this is a trace. And letting z be constant, we find the relationship between x and y at that constant z value. So this is z equals z naught, z equals z1, for whatever those z naught and z1 are. So let's do an example. Let's find and describe the level curves of this guy. So letting z equals z naught, we have z naught is x squared minus y squared. And let me just rearrange this. That's x squared minus y squared is, well, z naught. And what is this? Think back to the conic sections. This is a hyperbola. And note that when z naught is less than 0, then it flips orientation. It flips orientation in the following sense. Then we have x squared minus y squared is z naught, where z naught is now negative. And that implies that y squared minus x squared is negative z naught, where now negative z naught is positive. And recall that these two forms indicate orientation expanding along either the x-axis or the y-axis. So we have the following level curves. Note that when z naught is 0, then we have x squared minus y squared equals 0, and that implies that y is plus or minus x, and that is this green level curve, y is plus or minus x. When z naught is positive, then we have parabolas oriented or expanding along the x-axis, and the bigger z naught is, then the farther away the vertices of those hyperbolas are. If I said parabolas, I meant to say hyperbolas. And when z naught is negative, then those hyperbolas flip directions. And now the more negative z naught is, then the farther apart those hyperbolas get. So our level curves look something like that. Here is a better picture of them. And then from that, we can piece together what the surface looks like. And just as before, it's a hyperbolic paraboloid. Now, so far we've just done some level curves of quadric surfaces, but this is much more general, and in general we'll be doing multivariable calculus with, well, general functions. So let's find and describe the level curves of this guy. So this is z is equal to that. So we set z naught equal to e to the negative x squared minus y squared. Let's make an observation. Note that z naught must be between 0 and 1, since e to the anything is always non-negative, positive, and e to a negative number is always less than or equal to 1. And here that's always negative in the exponent because x squared and y squared are positive, so this is negative. And the largest that can be is 0, and recalling the graph of e to the x, then we are in this region. Yeah, so that's between 0 and 1. Okay, and then that means that the natural log of z naught is negative x squared plus or minus y squared, and thus x squared plus y squared is equal to negative natural log of z naught. Okay, recall the graph of the natural log. It looks like this. Here's 1. That's ln x. And we already know from this that we are in this region. And that means that ln is always negative here. And that means that this guy is actually positive, always. For every z naught that's in the range. So these are circles, and they are circles of increasing radius as z naught decreases. And why are they increasing as z naught decreases? Well, as z naught grows smaller and smaller, look here in the upper right, as z naught grows smaller and smaller, then ln of z naught grows larger and larger in magnitude, going to the negative side, but we're taking the negative of that. So the smaller z naught is, then the bigger it's the negative of its output. So we wind up with level curves that look like this, and we should label these. So we know that it has a maximum. That's the maximum of z naught equals 1. And that maximum occurs when this exponent here was 0. So that's when we are at x equals y equals 0. And then we'll have labels like z is 1/2 here, then something like 1/3, then maybe a quarter, etc. As z naught grows smaller and smaller, then these radii are increasing. And they'll only grow smaller and smaller, going down to 0 and never reaching it, since that was the range of our function. So take a moment and try to visualize what you think this surface looks like. Okay, here's a better picture of those level curves. And if you thought it's something like this, a mound, then you got that right. Z is at most 1, and then as z naught decreases, the circles are getting larger and larger in radius. Now, we can also take level curves of higher dimensional functions. We will occasionally have to deal with functions of 3 variables, and we'll be doing some clever things like thinking of functions of 2 variables as level surfaces of functions of 4 variables. Functions of 4 variables live in R4. Functions of 3 variables live in R4. They have an output in the 4th dimension, which we usually call W as the coordinate name. And they are naturally almost impossible to really visualize, since we cannot visualize 4 dimensions, but we can still see what their level surfaces look like. So the word level surface, that's just the higher dimensional analog of level curve. So let's do an example. Find the level surfaces of W equals square root of z minus x squared minus 2y squared. So we do this in the same way. So for level curves, we set z equals z naught and found what those traces essentially look like for different constant values of z equals z naught. Well, here now we let w equals w naught and find what the surfaces look like for different constant values of w. Seems I put a visualization here already, just to help out for where we're going with this. So instead of level curves, we'll wind up with whole surfaces now when we set w equal to different constant values. And here's what that looks like. So W naught is the square root of z minus x squared minus 2y squared. Thus, W naught squared is this. Okay, and you may recognize this as a paraboloid, and one can see that through rearranging. We have z equals x squared plus 2y squared plus W naught squared. And the way to look at this, okay, so first of all, this guy, that's a parabolic in both the x and y dimensions. And this guy, this is always positive, and that shifts the paraboloid up as W increases. And specifically, it shifts it up by W naught squared. So as we go from W equals 0 to 1 to 2 to 3, then the gaps are becoming larger and larger. So at W equals 1, then we begin at a z altitude of 1. When W is 2, we begin at a z altitude of 2 squared is 4, then a z altitude of 3 squared is 9, etc. So those are the level surfaces of this function of 3 variables, and that will be useful. I'll leave it at that. Even if, unlike level curves, we can't really piece together what this function truly looks like in 4 dimensions. And that concludes this short section on visualizing functions of 2 variables, or 3 in the last case. And we'll begin some calculus of functions of multiple variables in the next one. Have a great one.